So today's lesson involves a review of thermodynamic concepts that are important in fluid mechanics. One of the most prevalent ones is the ideal gas law, used for gases anyway, not very useful for liquids. But for gases, we have the old formula, PV equals nRT, P the pressure, absolute pressure. I'll get to what that means in the next lesson. V volume, N number of moles. R is my universal gas constant. You might recognize that guy, 8.314. And then T is the temperature. Again here, absolute temperature, meaning that it needs to be in kelvins if we're dealing with SI units, or Rankine if you're dealing with US units. Now this version of the ideal gas law isn't actually very useful in terms of fluid mechanics because we never really deal with the number of moles of a fluid. That's not really useful. So what we're going to do is change a little bit to get it into a better form that's much more useful in terms of quantities that we use in fluid mechanics. So first thing I'm going to do is divide by volume. So P is nRT over volume. And the next thing I'm going to do is multiply top and bottom by the molecular mass. I'm going to call that capital M. So there we go. I have this extra molecular mass on top. I put that with the number of moles, and then M on the bottom. Now, little n, number of moles, times the molecular mass, that's the actual mass of the gas. So I can replace N big M by just little m for the mass. So now I have mass of the gas, RT, over volume, and molecular mass, big M, mass over volume. Recognize that as density. And then I'm going to combine this universal gas constant with the molecular mass of the gas itself and call that a new constant. So now what I'm left with is that pressure P is density rho times R times T, and that is the version of the ideal gas law that's more useful in fluid mechanics because density is generally what we have, and so I want the density of the gas based on its pressure and temperature. So made it better for us because now we're dealing with density, but it also with that has a slight complication in that I have a new gas constant, still called the gas constant, R, but this gas constant is different for different gases. So it's still a constant in the sense that air always has the same value, carbon dioxide always has the same value, but those two values are going to be different. So R is really that value you're used to, 8.314, divided by the molecular mass of the gas. So if you want to know what it is, that's one way to find it. Another way is just look in the back of the book. The tables we're going to have R values for all the different gases, nitrogen, oxygen, air, whatever. They'll be in there. The next thermodynamic concept that is useful are specific heats. So the amount of energy you need to raise the temperature of an object per unit mass. And so there's two variations of this depending on how the heating is actually done, whether it's done at constant volume, in which case we have CV, or whether it's done at constant pressure, in which case we have CP. So it could be slightly different values depending on the process involved. And then other relationships for ideal gases, a change in internal energy, this is per unit mass, is just CV times delta T, change in temperature. The change in enthalpy, again per unit mass, is CP times delta T, change in temperature. And then this ratio of CP over CV is a constant for ideal gases. For air, value is 1.4. And then speed of sound, last relationship, speed of sound A is this ratio, CP over CV, times that gas constant R times T. So again, for air, that'd be 1.4. R value for air is 287 if we're in SI units, joules per kilogram Kelvin. And then the temperature, again, absolute temperature here. All thermodynamics need absolute temperatures in Kelvin or Rankine. So I'm going to finish off this lesson with a quick example. I have carbon dioxide, the density of 2.35 kilograms per cubic meter, at a pressure of 7.8 atmospheres. Want to know what the temperature is under those conditions. So the solution to this is going to be with the ideal gas law. Pressure is density times R times T. We're looking for the temperature, so I can rearrange that formula, divide by rho and R to get that temperature is pressure divided by density and my gas constant R. Now I know what the density is that was given to me. Need to know the value of R, so that is again just a constant, but I need to know what that number is for this particular gas, being carbon dioxide. So table B3, back of the book, has again a bunch of R values for a bunch of different gases. CO2 is in there. find the R value to be 189 joules per kilogram Kelvin for that guy. And then lastly, the pressure, 7.8 atmospheres. That's not exactly the units that we want for this. We want pascals. So 1 atmosphere corresponds to atmospheric pressure. So 1 atmosphere is 101.3 kilopascals, or 101,300 pascals. So 7.8 of those gives me 790,000 roughly pascals. So my temperature, that pressure, 790,140. Density, 2.35 kilograms per cubic meter. And then my R value, 189 joules per kilogram Kelvin, gives me 1779 kelvins. And then I can convert that into Celsius by taking away 273 degrees. So take away 273 degrees, gives me 1506 degrees Celsius for that temperature.